quantum attacks. So our objective is to move into PQC. Yesterday when I discussed this topic with Haman Khan, he is my collaborator. I told him that you should move into PQC in the future. So we have to stop working with panic security. PQC is the one and only solution for preventing the attacks which are performed by quantum computer. So our objective is to enter into post-quantum cryptography in the future. It can resist against all the attacks performed by quantum computer. The reason is PQC is also based on vector space. So PQC has 4 types of algorithms. First one is hash-based signatures. So this algorithm is used for generating the hash function, and it is used for performing a digital signature that can support authentication. And second one is multivariate cryptography. This is also based on PQC, and it is used for solving multivariate polynomial equations. And third category is board-based cryptography. In normal classical computers, we are performing error detection and error correction operations. Similarly, in quantum computer also, we can perform error detection and error correction operations using board-based cryptography. But compared to classical computers, in quantum computers, we need to send a lot of redundant bits in order to detect the errors. So it will take more number of redundant bits in board-based cryptography for detecting and correcting errors. Last one is lattice-based cryptography. That is the place we are going to work. We are going to start our work. Lattice-based cryptography means it is like a graph that consists of many lattice points. The points will be used for computing the private key, and the attacker should not be able to find the point because the point is not in a single dimension. It will be in multiple dimensions, and the intruder or attacker should not be able to find any lattice points in order to retain the security. And this is the top 5 countries that are working with PQC. First, China is taking lead. China is taking lead in all the 4 areas. In quantum computing, US is holding first and China is next. But post-quantum cryptography, China is the number 1 country in top 5 countries. Similarly, in quantum communications, also China is leading first. And quantum sensors, also China is leading first. But I am proud to say that India is holding top 5 positions in post-quantum cryptography. So what is quantum theory? Before I conclude my speech, I wanted to give some basic foundations for this quantum theory. What do we need to know to enter into quantum theory or post-quantum cryptography? We need to know 3 things. First thing is linear algebra. Everybody knows linear algebra. Second important component is a new notation which we need to know to enter into quantum computing. And third one is postulates. What is postulates? Postulates, I'll tell you later, but linear algebra plus a new notation plus postulates, these 3 things are mandatory to enter into quantum theory. If you know these 3 concepts clearly, it is easy to learn quantum theory. I'll tell you everything one by one. Postulates means set of rules. Like a protocol means a set of rules. Similar to that, postulates will take 3 things. First thing is how to define a state in quantum computing. Anything can be defined as a state. For example, at the time t1, what is the state of my laptop? So psi of t denotes the state of my laptop. Similarly, how do we need to perform the quantum operations on a particular state? So quantum operations can be done using some principles. We'll see that later. Third thing, how will you measure the outcome of the quantum may be any one of the vector, but which will be the outcome, which will be the output, that nobody can predict. That's why Feynman told that nobody is strong in quantum mechanics, because we cannot predict output of any operations. We have to use probability theory to measure the output of any operations in quantum computing. But classical computers are not like that. So postulates means you need to understand how to define the state of a system, how to do the quantum operations on a system, how to measure the output from the system. These are the three things required for understanding postulates. And new notation. I'll show you the new notation in the next slide. So this is the normal notation. Normally, in order to represent a vector, we will be using this notation. P is a vector. It can be a row vector or a column vector. So the first one is a row vector, and the second one is the column vector. Using this, we will be entering into a new notation. First notation is ket. This is called as ket. Ket means it is a column vector. And bra. Bra is the other notation. That is called as bra. Bra means it is a row vector in which all the entries are complex conjugate. So B1 is the complex conjugate, B2 is a complex conjugate, and so on. Bn is also a complex conjugate. So we need to understand that bra is a row vector, ket is a column vector. Using these two notations, it is easy to enter into quantum computing. How to convert a ket into a bra? In order to convert a ket into a bra, we have to take the transpose of the ket and compute the complex conjugate. We will get bra. Other than that, there are two more notations: inner product and outer product. Inner product is denoted like this. In Dirac notation, bra V into ket W, which is denoted here. Bra V into ket W is equal to B1 cap into W1 plus B2 cap into W2 and so on, Bn cap into Wn. So this is the direct notation. And if we have indirect notation, it is here. In direct notation, when you multiply a bra with a ket, we will be getting a complex number as the output. So B is a bra, W is a ket. When bra is multiplied with a ket, the output will be a complex number. But here, a ket is multiplied with a bra. If you multiply a ket with a bra, you will be getting a matrix as the output. The matrix size can be anything. So here, column size and row size can be anything. And these two are the basis vector.